Today, I want to speak about active and passive transformations of vector space over non-commutative algebra. We consider matrices whose entries belong to associative division the algebra A. According to the custom, the product of matrices A and B is defined as product of rows of matrix A and columns of the matrix B. If the product in the algebra is non-commutative, we cannot confine ourselves to traditional product of matrices, and we need to define two products of matrices. To distinguish between these products, we introduce a new notation. Let the number of columns of matrix A equal the number of rows of matrix B. Row-column product, or RC product of matrices A and B is form 5 to 1, or in matrix notation 5 to 2. Row-column product can be expressed as product of a row of matrix A and over a column of the matrix B.
A, CR, E.
Let the number of rows of matrix A equal the number of columns of the matrix B. Column row products, or CR product of matrices A and B is form 5 to 3, or in matrix notation can be expressed as equality 5 to 4. CR product can be expressed as product of column of the matrix A or the row of matrix B. We also consider following operation of the set of matrices. The transpose of the matrix A exchange rows and columns by inequality 5 to 5. Double transpose is original matrix. Also, we introduce the sum of matrices A and B by equality 5 to 7. We will use symbol RC or CR in name of properties of each product and in the notation. In order to keep this notation consistent with the existing one, we assume that we have in mind RC product when no clear notation is present. This rule will extend to following terminology. To draw symbol of product, we put two symbols of product in the place of index which participate in sum. For instance, if product of a numbers has form A circle B, then RC product of matrix A and B has form A circle B. We introduce RC power of the nth time n matrix A using equalities 24 and 25, where En is nth time n unit matrix. We introduce CR power of nth time n matrix A using equality 26 and 27, where En is n times n unit matrix. Let A be nth times n matrix. If there exists n times n matrix B such that equality 38 is true, then the matrix B is called RC inverse element of the matrix A. Similarly, let A be nth times n matrix. If there exists nth times n matrix B such that equality 40 is true, then the matrix B is called CR inverse element of the matrix A. Now we consider the definition of vector space over non-commutative algebra. Let A be associative division the algebra. Effective left side representation 1.1 of the algebra A in the module V is called left vector space over the algebra A. The number is called vector. The linear map 1.2 generated by left side representation 1.3 is called left side product of vector over scalar. The diagram of representation 1.5 describes left a vector space V. Here, the representation 1.4 corresponds to the product of vector V over scalar D, where D belongs to the field D. And representation G free form corresponds to the left side product of scalar A or vector V. The diagram of representation 1.5 holds commutativity of representations of commutative ring D and the algebra A in abelian group V. Equality 1.6. Following conditions holds for vectors. Commutativity law 1.7. Associative law 1.8. Distributive law 1.9 and 1.10. Unitarity law 1.11. Let A be associative division the algebra. Effective right side representation 1.15 of the algebra A in the model V is called right vector space or the algebra A. The number is called vector. The linear map 114 generated by right side representation 115 is called right side product of vector over scalar. The diagram of representation 117 describes right a vector space V. Here, the representation G14 corresponds to the product vector V over scalar D, and representation G3.4 corresponds to right side product of vector V over scalar A. The diagram of representation 1.7 holds commutativity of representation of commutative ring D and the algebra A in abelian group V. Equality 118. Let V be right a vector space. Following condition hold for V numbers. Commutativity law 119. Associative law 120. Distributive laws 121 and 122. Unitarity law 123. P and Q belong to the algebra A, and V and W belongs to a vector space V. Now we consider the definition of basis of vector space V over non-commutative algebra A. Let V be left a vector space. Let we have set of vectors Vi, where I belongs to I capital, the set of vectors. The expression wi, vi, here we assume the sum over index I, is called linear combination of vector vi. A vector w equals sum of wi, vi is called linearly dependent on vectors vi. Since the equation 7 to 12 imply existence of index I equal j, such that wj not equal 0, then the vector vj linearly depends on the rest of vectors v. The set of vectors vi of left I vector space v linearly independent if w equals 0 follows from the equation 213. Otherwise, the set of vectors vi is linearly dependent. The set of vectors E is a basis of left a vector space V if vectors EI are linearly independent and any vector V in vector space V linearly depends on vectors EI. Let E be the basis of left a vector space V and vector V has expansion 214 with respect to the basis E. A numbers VE are called coordinates of vector V with respect to the basis E. Matrix of A numbers V is called coordinate matrix of vector V in basis E. Coordinates of vector V related to the basis E of left a vector space are uniquely defined. We just considered the definition of the basis of left a vector space. Similar way, we may consider definition of basis of right a vector space. When we considered the definition of left a vector space, we mentioned that we can consider the set of coordinates of vectors with respect to given basis as coordinate matrix. There are different ways to represent the coordinate matrix of given vector. Depending on this, we may consider different type of vector space. Now we consider the left vector space over algebra A. We represent the set of vectors v1, vm as row of matrix V and the set of A numbers c1, cm as column of matrix C. Thus, we can represent linear combination of vectors v1, vm as CR products for that 2. In particular, if we write vectors of basis E as row of matrix 4.3 and coordinate of vectors W with respect to basis E as column of matrix 4.4, then we can represent the vector W as CR products of matrix 4.5. Corresponding representation of vector space V is called left a vector space of columns, and V numbers is called column vector. We consider the set of coordinate of vectors as column matrix. For the same way, we can consider the set of vectors as row matrix. We represent a set of vectors v1, vm as column of matrix V, and the set of A numbers c1, cm as row of matrix C. Thus, we can represent linear combination of vectors v1, vm as RC product of matrices 4.7. In particular, if we write vectors of basis E as column of matrix 4.8 and coordinates of vector W with respect to basis E as row of matrix 4.9, then we can represent the vector W as RC product of matrices 4.10. Corresponding representation of vector space V is called left a vector space of rows, and V number is called row vector. We considered two types of left a vector space. Similar way, we can consider two types of right a vector space. Now we consider the right vector space. We represent set of vectors v1, vm as row of matrix V, and a set of A numbers c1, cm as column of matrix C. Thus, we can represent linear combination of vectors v1, vm as RC product of matrices 412. In particular, if you write vectors of basis E as row of matrices 413 and coordinate of vector W with respect to basis E as column of matrix 414, then we can represent the vector W as CR product of matrices 415. Corresponding representation of vector space V is called right a vector space of columns, and V number is called column vector. Now we consider another type of vector space, and we represent the set of vectors v1, vm as column of matrix V, and the set of A numbers c1, cm as row of matrix C. Thus, we can represent linear combination of vectors v1, vm as CR product of matrices for 17. In particular, if we write vector of basis E as column of matrix 418 and coordinate of vectors W with respect to basis E as row of matrix 419, then we can represent the vector W as CR product of matrices 420. Corresponding representation of vector space V is called right a vector space of rows, and V number is called row vector. Choice of type of vector space is agreement required to solve a specific problem and depends on the problem that we need to solve. Homomorphism of any algebra is the map which preserves the main property of this algebra. This is why very important to know the structure of homomorphism. In particular, we now start to learn homomorphism of vector space over non-commutative algebra. The homomorphism F of left a vector space satisfies equalities 1.1 and 1.2, where VW belongs to a vector space V and A belongs to the algebra A. The difference between homomorphism of left a vector space and its linear map is very important. For homomorphism, inequality 1.2, we have product over a number. But for linear map, inequality 1.2, we have product over element of field D over which algebra A is defined. So, any homomorphism is linear map, but not every linear map is homomorphism. In particular, for linear map, you can define polylinear map and tensor product, but for homomorphism, you cannot introduce polymorphism. Below, we will consider some property of homomorphism of left vector space over non-commutative algebra A. Let V, W be left a vector spaces of columns. Let the set of vectors EV be a basis of left a vector space V. Let the sector of vectors EW be a basis of left a vector space W. Then homomorphism F of left a vector space has presentation 1.3 or 1.4 relative to selected basis. Here, A is coordinate matrix of vector A related to the basis EV. B is coordinate matrix of vector B, which is image of vector A related to the basis EW. F is coordinate matrix of set of vectors of image vectors EV related to the basis EW. The matrix F is unique and is called matrix of homomorphism F relative basis EV EW. Similar statement is true for left a vector space of rows. The difference is only that instead of equality 1.3, we have equality 1.5, and instead of equality 1.4, we have equality 1.6. This is because we have different presentation of the vector. We consider the proof of theorem 1.3. Vector A in V has expansion 1.7 related to the basis EV. Vector B in W has expansion 1.8 related to the basis EW. Since F is homomorphism, then we can use equalities 1.1 and 1.2. Equality 1.9 follows from equalities 1.1 and 1.2. Here we use that vector A has expansion 1.7 relative to the basis EV, and image of linear combination is linear combination of images. Image of vector EVI of the basis EV is vector of left a vector space W and has expansion 1.10 related to the basis EW. Fi is image of vector EVI related to the basis EW and has coordinates Fji relative to this basis. The equality 1.11 follows from equality 1.9 and 1.10. The equality 1.4 follows from comparison of 1.8 and 1.11. Because coordinates of vector related to the basis are defined uniquely, it follows that B equal A CRF. We finish the proof of the theorem. Now we consider the converse theorem. Let V, W be left a vector spaces of columns. Let the set of vectors EV be a basis of left a vector space V. Let the set of vectors EW be a basis of left a vector space W. Let F be matrix of A numbers. Let the map F, defined by equality 117, is homomorphism of left a vector space of columns. Homomorphism F, which has the given matrix F, is unique. Here we defined the coordinate of image of vector A as CR product of matrix A and matrix F. From properties of product of matrices, it follows that image of sum of vectors is sum of images, and image of product of vector over scalar is product of scalar and image of the vector. According to the definition of homomorphism, the map F is homomorphism of left a vector space of columns. Let F be matrix of homomorphism F and G relative to basis EV, EW. From the definition of homomorphism F, it follows that homomorphism F equal homomorphism G. On the basis of considered theorems, we identify the homomorphism F of left a vector space of columns at the matrix of representation 117. Homomorphism of left a vector spaces is called isomorphism between left a vector spaces V and W if inverse correspondence is homomorphism. A homomorphism in which source and target are the same left a vector space is called endomorphism. Endomorphism F of left a vector space V is called automorphism if inverse correspondence is endomorphism. A similar way, we may consider homomorphism of right A vector space. The homomorphism F of right A vector space satisfy equalities 2.1 and 2.2, where V and W are vectors and A belongs to algebra A. And again, I want to put attention to the difference between homomorphism and linear map, because for linear map, we have inequality 2.2 element of field D. The theorems that we considered for left vector space, we may consider also for right vector space. We just look for this theorem, but will not prove them because proof is very similar. Let V and W be right A vector spaces of columns. Let the set of vectors EV be a basis of right A vector space V. Let the set of vectors EW be a basis of right A vector space W. Then homomorphism F of right A vector space has presentation 2.3 or 2.4 related to selected basis. Here, A is coordinate matrix of the vector A related to the basis EV. B is coordinate matrix of image of vector A related to the basis EW. F is coordinate matrix of set of images of vectors of basis EV related to the basis EW. The matrix F is unique and is called matrix of homomorphism F relative to the basis EV and EW. Similar statement is right for right a vector space or rows, but instead of equality 2.3, we have equality 2.5, and instead of equality 2.4, we have equality 2.6. Converse theorems also are true. Let V, W be right a vector space of columns. Let the set of vectors EV be a basis of right a vector space V. Let the set of vectors EW be a basis of right a vector space W. Let F be a matrix of A numbers. Then the map F, defined by equality 217, is homomorphism of right a vector space of columns. The homomorphism F, which has the given matrix F, is unique. A similar theorem is true for right a vector space of rows, but instead of equality to 17, we have equality to 18. On the basis of considered theorems, we identify the homomorphism F of right a vector space of columns and the matrix of its representation to 17. Now we will consider the definition of sum and product of homomorphisms of A vector spaces and corresponding operation with their matrices. Let V, W be left a vector spaces and maps G and H be homomorphism of left a vector space. Let the map F be defined by equality 3.1. The map F is homomorphism of left a vector space and is called sum of homomorphisms G and H. Let V, W be left a vector spaces of columns. Let EV be a basis of left a vector space V. Let EW be a basis of left a vector space W. The homomorphism F is sum of homomorphisms G and H if and only if matrix F of homomorphism F relative to basis EV, EW is equal to the sum of the matrix G of the homomorphism G relative to the basis EV, EW, and the matrix H of the homomorphism H related to basis EV, EW. I don't stop on the proof of this theorem because the proof is very simple. Let U, V, W be left a vector spaces. The diagram of maps for that one be commutative diagram where map GH are homomorphism of left a vector space. The map F is homomorphism of left a vector space and is called product of homomorphisms H and G. Let U, V, W be left a vector spaces of columns. Let EU be a basis of left a vector space U. Let EV be a basis of left a vector space V. Let EW be a basis of left a vector space W. The homomorphism F is product of homomorphism H and G if and only if matrix F homomorphism F related to the basis EU in W is equal to the CR product of matrix G of homomorphism G related to the basis EU EV over matrix H of the homomorphism H related to the basis EV EW. We use equality for that 9 to express the relation between matrices F, G, and H. Similar statement is true for right a vector space of columns, with only difference that instead of CR product, we have RC product, equality 4 to the 10. To prove theorem is enough to point that homomorphism F has representation for 11, homomorphism G has representation for 12, and homomorphism H has representation for 13. Summarize all this, we have equality for 14, from where equality for that 9 follows. To verify that map F is homomorphism is very simple, and we will not delay on this statement. Now, after a long journey, we finally near our destination. In this part of my lecture, I will introduce basis manifold of finite-dimensional vector space over non-commutative associative division algebra A. Let V be left a vector space of columns. Let a set of vectors E1 and E2 be a basis of left a vector space V. If the power of the set I and power of the set J are finite numbers, then power of the set I equal power of set J. Shortly speaking, the power of the finite set is the number of elements of this set. Let the power of set I equal m and power of set j equal n, and let m will be less than n. Because E1 is a basis, any vector e to j of basis E2 has expansion relative to basis E1. Because E2 is basis, then equality 1.2 should follow from equality 1.3. Instead of E2, substitute its representation relative to the basis E1. Because E1 is the basis, we get equality 1.4. According to the statement 1.1, CR rank of the matrix A not greater than M. A system of linear equation 1.3 has more variables than equations. According to the theory of linear equations, we get the statement lambda not equal 0, which contradicts the statement 1.2. Therefore, statement m less than n is not valid. In the same manner, we can prove that the statement n less than m is not valid. Please complete the proof of the theorem. We call the dimension of left a vector space the number of vectors in a basis. Let V be a left a vector space of columns. The coordinate matrix of basis G, relative basis E of left a vector space V is CR non-singular matrix. The statement of theorem follows from the statement that CR rank of the coordinate matrix of basis G, relative basis E, equal to the dimension of left a vector space of columns. Similar theorem is true for left a vector space of rows. Let V be left a vector space of rows. The coordinate matrix of basis G, relative basis E of left a vector space is RC non-circular matrix. We see that we use here different type of the product. Let V be a left a vector space of columns. Let E be a basis of left a vector space V. Then any automorphism F of left a vector space V has form 113, where F is a CR non-singular matrix. Similar statement also true for left a vector space of rows. And any automorphism F of left a vector space V has form 114, where F is RC non-singular matrix. Both theorem follows from the theory of system of linear equations over non-commutative algebra. Matrices of automorphisms of left a vector space V of columns form a group GL N CR A. Here we introduce notation for the set of automorphism of left a vector space V. Similarly, matrices of automorphism of left a vector space V of rows form a group GL. To prove the theorem is enough to write representation of automorphism. If you have two automorphisms F and G, then you can write V prime equal V CRF, V prime prime equal V prime CRG equal V CRF CRG. Therefore, the resulting automorphism is matrix F CRG. Let V be a left a vector space of columns. Let E be a basis of left a vector space V. Then any automorphism F of left a vector space V has form 113, where F is CR non-singular matrix. The equality 113 follows from equality 1.4. Because F is an isomorphism for each vector V prime, there exists one and only one vector V such that V prime is image of the vector V. Therefore, the system of linear equation 113 has a unique solution. According to the theory of system of linear equations, F is CR non-singular matrix. Similar theorem is true for left vector space of rows. If E is a basis of left vector space V, then any automorphism F of left vector space V has form 114, where F is RC non-singular matrix. Matrices of automorphism of left A vector space V of columns form a group GL and CRA. Here introduce notation for the set of automorphism of left vector space V. The proof of this theorem is based on the previous theorem, where we show that automorphism of vector space has presentation 113. We show this presentation for each automorphism F and G and put one equality into another. Since matrix of automorphism is unique, then we have conclusion that product of this automorphism has form F CR G. Similar theorem is true for left vector space of rows. Let V be a left vector space of columns. We prove above that if we select a basis of left vector space V, then we can identify any automorphism F of left vector space V with CR non-singular matrix F. Corresponding transformation of coordinates of vectors is called linear transformation. Similarly, we can tell about left vector space of rows, because if we select a basis of left vector space V, then we can identify any automorphism F of left vector space of rows with RC non-singular matrix F. Corresponding transformation of coordinates of vectors is called linear transformation. Summarizing statement that we get above, we can prove the theorem. Let V be a left vector space of columns, and E the basis of left vector space V. Automorphism of left vector space of columns form a right-side linear effective representation of group GL and CRA. Similar theorem is true for left vector space of rows. Automorphism of left vector space of rows form a right-side linear effective representation of group GL and RCA. Automorphism A acting on each vector of basis of left A vector space maps a basis into another basis. Based on this theorem, we can extend right-side linear representation of group GL and CRA to the set of bases. Transformation of this right-side representation is called active transformation. Based on this theorem, we can extend a right-side linear representation of group GL and CRA in left vector space V of columns to the set of bases of left vector space V. Transformation of this right-side representation on the set of bases of left vector space V is called active transformation, because the homomorphism of the left vector space induced this transformation. According to the definition, we write the action of the transformation A on the basis E as E CR A. From the equality 211, it follows that endomorphism of left a vector space and corresponding active transformation act synchronously, and coordinate of the image of vector V with respect to the image of the basis E are the same as coordinate of the vector V with respect to the basis E. Active right-side representation of group GL and CRA on the set of bases is single transitive representation. The set of bases identified with trajectory of active right-side representation of group GL and CRA is called the basis manifold of left a vector space V. Group GL is the most general group of homomorphism which preserve the properties of vector space over algebra A. However, sometimes we need to consider additional properties of vector space like scalar product of vectors. In this case, we need to consider only those homomorphisms which preserve this special property as well. Such homomorphism also generate group which is subgroup of group GL. Such group G we call symmetry group. Without loss of generality, we identify element G of group G with corresponding transformation of representation and write its action on vector V as V CRG. In case of left vector spaces of columns, or VRCG in case of left vector spaces of rows. The right side representation of group G in left a vector space is called linear G representation. Like in case of group GL, we call right side representation of group G in the set of bases of left a vector space active left side G representation. Not every two bases can be mapped by a transformation from the symmetry group because not every non-singular linear transformation belongs to the representation of group G. For instance, if we consider scalar product of vectors, there are linear transformations which doesn't concern scalar product. Therefore, we can represent the set of bases as union of orbits of group G. We call orbit E CRG of the selected basis E the basis manifold of left a vector space V of columns. Similarly, we call orbit E RCG of the selected basis E the basis manifold of left a vector space of rows. From theorem considered above follows theorem 211. Active right-side G representation on basis manifold is single transitive representation. For any non-commutative group, we may consider left side and right side representation. If left side representation F of group G on algebra A2 is single transitive, then we can uniquely define right side representation H on the same algebra such a way that considered diagram is commutative. Applying this statement to active representation of the symmetry group, we get the following theorem. On the basis manifold E CRG of left a vector space of columns, there exists single transitive left side G representation commuting with active. Similarly, on the basis manifold ERCG of left a vector space of rows, there exists single transitive left side G representation commuting with active. Transformation of left side G representation is different from an active transformation and cannot be reduced to transformation of space V. A transformation of left side G representation is called passive transformation of basis manifold
ECRG
of left a vector space of columns, and the left side G representation is called passive left side G representation. According to the definition, we write the passive transformation of basis E defined by element A as
A CR E.
the coordinate matrix of basis E prime relative basis E of left a vector space V of columns is identical with the matrix of passive transformation mapping basis E to basis E prime. Similar theorem is true for left a vector space of rows. The coordinate matrix of basis E prime relative basis E of left a vector space V of rows is identical with the matrix of passive transformation mapping basis E to basis E prime. According to this theorem, we can identify a basis E prime of the basis manifold E CRG of left a vector space of columns and the matrix G of coordinate of basis E prime with respect to the basis E. Since E prime equal E, then equality 214 gets form 214. Based on equality 214, we'll use notation En CRG for basis manifold E CRG. An active transformation changes bases and vectors uniformly, and coordinates of vector relative bases do not change. A passive transformation changes only the basis, and it leads to change of coordinates of vector relative to basis. Let V be a left a vector space of columns. Let passive transformation G map the basis E1 into the basis E2 equals V dot 1. Let Vi be matrix of coordinate of vector V with respect to the basis EI, E equal 1 or 2. Coordinate transformation 3.2 or 3.3 do not depend on vector V of basis E, but is defined only by coordinate of vector V relative to basis E. Similar statement is true for left vector space of rows. Let V be a left a vector space of rows. Let passive transformation G map the basis E1 into the basis E2 equality 3.4. Let Vi be matrix of coordinate of vector V with respect to the basis EI, EI equal 1 or 2. Coordinate transformation 3.5 or 3.6 do not depend on vector V of basis E, but is defined only by coordinates of vector V relative to the basis E. According to theorem that we considered above, coordinate of vector v has representation 3.7 with respect to basis E1 and basis E2. Since basis related by transformation 3.1, we get equality 3.8. The coordinate of transformation 3.2 follows from the equality 3.8. Because G is CR non-singular matrix, coordinate transformation 3.3 follows from the equality 3.2. Coordinate representation 3.3 that we considered above for effective linear right side contravariant G representation, which is called coordinate representation in left a vector space of columns. Coordinate transformation 3.3 for effective linear right side contravariant G representation, which is called coordinate representation in left a vector space of columns. Similar theorem, coordinate transformation 3.6 for effective linear right side contravariant G representation, which is called coordinate representation in left a vector space of rows. Similar definitions are true for right vector spaces over non-commutative algebra A. Our adventure into the theory of vector spaces over non-commutative algebra A comes to its final point. Now we will consider the definition of geometrical object in vector space. Let V, W be left a vector spaces. For simplicity, we assume that A vector spaces V and W have the same type. Let the map of group G to the group of passive transformation of left a vector space W be coordinated with the map of group G to symmetry group of left a vector space V. This means that passive transformation f of G of left a vector space W corresponds to passive transformation G of left a vector space V. Let V and W be left a vector space of columns, and coordinate transformation in left a vector space V has form 1.1. Then coordinate transformation in left a vector space W gets form 1.2. Matrix W is called coordinate matrix of geometric object with respect to the basis EV, and vector W is called representative of geometric object in left a vector space V. The covariance principle states that representative of geometrical object does not depend on the choice of the basis EV. If you have some questions about vector spaces over non-commutative algebra, you can post your question on the website with this video. Thank you.